topics that were presented so far. It's about branes in string theory. I'll call the lecture Branes and Supersymmetric gauge theories. We will not have too many equations. Instead, we will draw many pictures and use the notion of a quiver, which is some shorthand notation for a gauge theory, we will see. And I'll also ask for many questions during my talk. So if you have any question, please feel free to ask. Stop me at any time, and I will encourage questions as we go. Okay? So I'll start by giving a motivation. So in type 2 string theory, we have a whole zoo of branes. There is the fundamental string. We heard from Massimo a lecture yesterday about computations which are done on the fundamental string. This is where we start. But there are other branes. There is the magnetically dual, which we will denote as the Navier-Schwarz 5 brane. There are the D-branes. And P can run between -1 and 9. So there's a whole set of those branes. And we will use many of them during our discussions. In M theory, you'll have the M2 brane and the M5 brane. And they are related to these branes by a collection of dualities. And our goal is to try to understand the dynamics of those branes, what kind of physics we can extract. There is some low energy quantum field theory. Most of the time it's a gauge theory on the whole volume of the brane. And when we try to characterize such a theory, let's say we find such a theory, we gain two things. The first thing is that if we have such a theory, it gives us an idea of the dynamics that such a brane system has. The other point is that if I understand something about the brane dynamics, the way the branes behave, then I gain something about the physics of this gauge theory. So it goes in both directions, and it's a very fruitful area of research. Any questions so far about what I said? So these are conceptual points, not too many equations. If you ever thought maybe there are some questions, let me know. So what we're going to do is to take some arrangements of branes, constructions of branes, and figure out the low energy dynamics. And the first object which we will do is to take a DP brane. It has a theory, U1 vector multiplet in P+1 dimensions with 16 supercharges. And the vector multiplet contains a gauge field, 9 minus p scalars, and fermions, which I will not be specific about. We will just leave it like that. In terms of picture, what we can do is if I have a DP brane like here, I can draw it in this way with 2 directions. This is going to be the direction where the brane spans. So it's a p, 1 space-time, p space, 1 time. And there will be the transverse directions, 9 minus p of them. And so in this graph over here, the brane will be represented by a straight line, right? So it's infinite in extent in the parallel directions, and it's point-like in the transverse directions. The scalar fields should be associated with the positions of the brane. In 9 minus p dimensions. And here we have some nice example of the Broglie relation. Which tells us that on the one hand, I find a scalar field in p plus 1 dimensions. So x is a point in R p, 1. And, well, let's call it xc instead of x. So this is a direction along the world volume. And on the right-hand side, what we do, we write a distance. So let's call it x, which is just the position of the brane in 9 minus p dimensions. This has dimensions of length. This has dimension 1, typically, because it's in a vector multiplet. And therefore, there should be a relation L string squared. So the Broglie relation, remember that it tells us that momentum is related to the wave number by a fundamental constant. And here we also have this relation between a scalar field, which can admit vacuum expectation values in a quantum field theory, and a position of the brane in space-time. And the constant of proportionality is a fundamental constant. Any questions about this point? Okay, so the gauge theory that lives on those branes has 16 supercharges. Next thing we will do is to take n dp branes and we can draw them like that. Again, the same graph that we are using, R p, 1, R 9 minus p. And I have positions of branes, x1, x2, and so on. Okay? So what's the important physics of this theory? So individually, these branes have a U1 gauge symmetry. But when we take them to be coincident, we get an enhanced gauge symmetry, which is what we call the adjoint Higgs mechanism. Okay, so U1 to the n gets enhanced to UN, gauge symmetry. And now we have a non-abelian gauge symmetry living on the branes in p+1 dimensions. Right? So by studying the various brane configurations that such a system has, we can get some idea about the physics of this gauge theory. In particular, let me introduce the notion of the modular space. So the modular space of vacua is the modular space where all brane system, all brane configurations can be admitted, right? The U1 gauge symmetry. So the best way to argue about such a gauge symmetry is to think about the Gauss law. Suppose that I have a fundamental string which ends on the D-brane. This is the basic definition on the D-brane. It's the boundary of a fundamental string. If I have such a thing, and I'm an observer which lives in the space-time of the brane, then if I'll draw, this is the world volume of the DP brane. This is the endpoint of this fundamental string. What I'm going to do is to take a sphere which surrounds this, and then I'll perform flux experiment, right? So I'll integrate over the flux lines which are emanating from this point particle. And what I'll find is the Gauss law. Integral star of f over the sphere, and the sphere we are in p+1 dimension, so this is going to be a p sphere, right? And so just by the fact that a fundamental string ends on a dp brane, it tells me that there must exist a gauge field which will absorb the flux lines that are generated by the end of the string, right? So now I get that there is a U1 gauge field on the world volume of the dp brane. And by supersymmetry, since this brane preserves 16 out of 32 supercharges, it implies the existence of all the other fields in the supermultiplet, scalar fields and fermions. Does this answer your question? Okay, more questions? Very good. So we are back to the system of n branes, and they can do many things. They can be placed on the same position. We will call this coincident. They can be separated, each brane in a different position. And we have a space of all possible positions. All of these branes are don't exert any force on each other, every brane configuration that I pick will have a zero force condition, and this will correspond to the vacuum of the corresponding quantum field theory. And therefore, we get a nice correspondence between the moduli space of vacua and the space of all possible positions. This is the first geometric correspondence that we see here, that on the one hand, we have that branes have a quantum field theory living on the world volume. On the other hand, they are a geometric object in space-time, and therefore there is a natural correspondence between branes and geometry. Any questions about this point? Okay. The reason there is no force is because we have a maximal amount of supersymmetry when it comes to theories that contain no gravity. So it's just because of the supersymmetry that it doesn't allow for forces to show up. As we saw in the lectures on supersymmetry, the interaction terms show as integrations over several theta components. And because of this supersymmetry, I'll need more theta components, and so they will not give me any contribution to the superpotential. Excellent questions. Very good, excellent. So that's the other approach. So branes are not just objects which have gauge theory on the world volume. They are also some objects in space-time which are just classical solutions of space-time. They share interactions between the different massless fields that we have in type 2 string theory. We have gravitons, we have the Ramon-Ramon forms, we have the dilaton. All of them can serve as exchanging forces between those different objects. When we think of these branes as just classical solutions of type 2 string theory. And as such, when I think of it in this way, the forces, gravitational attraction, and the scalar field exchange, the dilaton exchange attraction, gets cancelled precisely by the fact that they carry the same charge, and therefore I should have Ramon-Ramon repulsion, right? So the sum of repulsion plus attraction will be exactly 0, and this is guaranteed by the amount of supersymmetry. So we are discussing conceptual points. There are not too many equations. It's just a question of understanding the essence of those brane systems. So it raises a lot of questions. Please feel free to ask as you wish. Good. So modular space of vacua is the space of all possible positions. So let's try to compute this thing. So every brane has a set of 9 minus p positions. And I'll have n of them, so I'll just take the power of n. But these are identical objects. So I'll have to divide by the action of the symmetric group. So that's a quick derivation of the modular space of vacua of a supersymmetric gauge theory with 16 supercharges. Okay? Any questions about this derivation? Something very interesting happens when two of these points coincide. So let's draw this space. Now we are in 9 minus p dimensions. And in 9 minus p dimensions, the branes look point-like, and they can be anywhere. And something interesting happens when the branes coincide. Now I have a fixed point of the symmetric group action. If I will exchange the position of these two, I'll get the same configuration. So at fixed points, of the Sn action, I get extra muscle states. And the gate symmetry is enhanced. Okay, and how does it go? So we will pick a partition Ni of n such that sum over I Ni is equal to n, and then the gate symmetry is enhanced from U1 to the n, which is the gate symmetry when all the branes are separated, to a product over I, U and I. And in particular, at the most singular point, where all of the branes coincide, there's going to be only one gauge group. The set of such gate symmetries is called a Levy subgroup. Of UN. And Levy was an Italian mathematician. He discovered the joint Higgs mechanism way before we were understanding the notion of Higgs mechanism. Any question about this point? Yes. Right. Excellent question. Yes. Right. So for in backgrounds, with OP planes, I will get an orientable P-plane. So its role for us would be just to reflect space-time. So a point over here is identified as a point over here, right? There is also an rotation reversal, but it's not so crucial for our purposes now. And if I have a collection of branes, which are parallel, then I should check what kind of symmetries do I have, right? So there's one symmetry which just permutes. So if I have n of them, there is a natural Sn. Now, there's also the reflection symmetry just tells me that if I will take the brane or its image, I will get the same type of physics. So there is a collection of Z2s. Those actions of the Z2 and the Sn do not commute. So it's typically denoted as Z2 to the n, like that. If you want, there is. Okay, this is the Weil group of, depending on the choice of the orientable plane, of either SPN, SO2n, O2n, or O2n plus 1. Okay? Any questions about this point? That's an advanced question. So if you are familiar with Lie algebras, and also with orientable planes. I didn't explain so much, then it's fine. Otherwise, if you have questions, please go ahead and ask the questions. No, I didn't plan to do that. It's only because I got a question about it. So I prefer to discuss the features of brain systems without orientable planes. When you put in orientable planes, it's a very interesting story. It's plenty of details, which are very good. After all, gauge theories are all about the details. And so it's a lot of fun to study backgrounds with orientable planes, but first we need to make sure that we understand what happens in the absence of such planes. Yes?
I would guess that this model could be irrelevant overall translation and overall rotation that you would want to quotient it.
Mm-hmm. So, very good. So indeed, this moduli space is has one modulus which over which the action of the group is trivial, right? Because if I take the center of positions in R9 minus P, that's an invariant under the symmetric group. So indeed, this moduli space divides into a trivial R9 minus P. So trivial SN action. And the remaining moduli, remaining positions, are the distances between the branes, and those distances are acted by the symmetric group. And minus 1 divided by Sn, and this n minus 1 is the fundamental representation of the symmetric group. If you are familiar with representation theory of symmetric groups. Any questions? Excellent questions, actually. Keep on raising them. It's every such question brings about very interesting physics and discussions that you could have. So, so here's our brain system. Let me just make a point here. We saw that brains are geometric objects, but brains are also algebraic objects. Because I have a very natural way of embedding all possible Levy subgroups. I just computed all possible Levy subgroups of the algebra UN. I can repeat the story for other algebras, and I will get similar results. Okay? So brains are physical objects. They are objects in space-time. They are classical gravitational solutions. They are geometric objects. This correspondence. And they are also algebraic objects. Which brings about that if you want to understand brain physics, you want to understand both the algebraic aspects and the geometric aspects. Altogether, they form into a mathematical field of algebraic geometry, and so there is a very fruitful interaction between the study of supersymmetric gauge theories and algebraic geometry. Any questions? So so far we dealt with D-branes. Now I'm going to put some more ingredients. And I'll take the Navier-Schwarz 5 branes. They have a very interesting feature. So here's the Navier-Schwarz 5 brane. I'll just denote it by an S. So here's the brane. I'll need to use colors because now I'm going to have two types of branes. Here's a DP brane. Okay? So the DP brane has the feature I shouldn't write with this. Sorry for that. DP brane ends on a Navier-Schwarz 5 brane. Just like this idea that we got used to many times, that a fundamental string ends on a DP brane. So compare this to fundamental string ends on DP brane. And what we argued before when we were discussing over here is that the fundamental string serves as the electric object to an observer living on the DP brane, but because of the usual notions of Maxwell theory, wherever I have an electric source, I should also expect a magnetic source. So let's try to revisit the problem over here. What would be the magnetic source? So this is an electric source. Magnetic source should be a codimension 3 object. And should be a codimension 3 independent of P. So for any value of P, I should find an object which ends on the brane and serves as a magnetic source for the observer living on the DP brane, right? Just because of the fact that I have a gauge field living on the world of the brane. This is related to your question from before, right? Any ideas? So I'm going to just state it. DP minus 2 ending on the DP brane is the right object. The boundary of the DP minus 2 brane is a P minus 3 brane, and it's a codimension 3 object in P plus 1 dimensions. Right? So this is the magnetic source, DP minus 2, or the end of DP minus 2. Any questions about this thing? So yes. Excellent question. I mean, we will also have to impose boundary conditions for the end of the P brane inside. Yeah, you could take the usual the P brane action. So you take it for a single P brane and just think about P brane with a boundary, right? So we will have to just repeat the story, just like we do it with fundamental string, with world sheets, which has boundaries. Here we will just do it with p+1 dimensional objects with p-dimensional boundaries. Yes, except that it's heavily restricted. So, for example, fundamental string cannot end on a Navier-Schwarz 5 brane. It can only end on a D-brane. And the p-2 brane ends on a dp brane. Cannot end on another p brane. Just because when I look at such an experiment of a Gauss law, there's only one gauge field, and therefore only one electric excitation, and only one magnetic excitation. So it's a fundamental string as the electric excitation, and the p-2 brane as the magnetic excitation, and that's it. No other branes are allowed to end. This is very crucial. That's right, and it's pretty much done by dimensional analysis. It seems to be enough. Here, actually, it's from 0 up to 6. Right? Excellent question. So I'll draw so I'll set the directions of the actually no, I don't want this. So for D6 on ending on Navier-Schwarz 5, the space-time divides into R6. This is the world volume which is common to both. Then there is an R, so it's R15. Then there is an R, and then there is R3. Okay? So I'm going to pick as my coordinates as R in this direction and R3 in this direction. Okay? And the NS brane spans here. The D6 is here, and R3 is transverse to both. Okay? So in this frame, I'll draw it like this. Here's a D6 brane, and here is Navier-Schwarz 5 brane. Navier-Schwarz 5 brane is point-like. It's in this reference frame. Both R3 and R are transverse to the NS brane, so it looks point-like, and the D6 brane spans over R, but is point-like in R3. And so here's a situation where a D6 ends on the Navier-Schwarz 5 brane. What does Gauss' law tell me? There's still a Gauss' law. Gauss' law tells me that the net charge of 6 branes on the left must be equal to the net charge of 6 branes on the right. Right? So if I have N1 D6 branes ending on the left, N2 ending on the right, then they must be equal. This is going to be improved if I will introduce a non-zero background of cosmological constant. But I don't know how much people are familiar with this thing. This is the more general result. So certainly there could be configurations of 6 branes which end on the Weschwarz 5 branes. Any questions? It's yeah. F10. It's called the Romance mass. And it's the electric field that is turned on whenever you have a background with 8 branes. Right, the 8 brane is a domain wall in 10 dimensions. It splits space-time into 2 parts, before and after. And as we know very well from electrostatics, when we learn about electrostatics, when we learn about the physics of capacitors, the electric field jumps across a plate of a given charge, and the jump in the electric field is proportional to the charge. That's a completely analogous effect that we have if we have 8 brane which divides space-time into 2 parts. The electric field jumps across these 2 parts by an amount which is proportional to the charge. No, it doesn't have to be inside. It could be away. I mean, so imagine a situation where here's a D8, and here I have an electric field of amount m. Here I have, let's call it m right, m left. So what I know is that m right minus m left is equal to 1. So I pick a unit in which the jump is 1. So here's a medium where the electric field has some value, m, and in this medium I can put an Weschwarz 5 brane, and then I'll have to satisfy this relation. Right? The electric field goes over the whole medium. That's the reason also it's called cosmological constant, because it's constant in any point of space-time, and so gives a contribution which is just the square of this value to the cosmological constant. More questions? I mean, I did not plan to get into this, but you know, there will be plenty of fascinating things we can say about each of those questions that you're asking me. Cannot, just doesn't allow, right? I mean, the P brane has only one gauge field on it, and we already occupied the 2 objects that satisfy the electric source and magnetic source. So we are done. If you want to have other objects to end on the DP brane, we will have to introduce more quantum fields living on the world volume. More excitations. These are just the simple rules of electromagnetism. More questions? So I will take one more point about branes ending on branes. I'll take that at the 3 brane. Oh, okay. I wrote it over here. The P brane ends on the Weschwarz 5 brane, and in particular, if I pick P equals to 3, so the NS5 brane has a 6-dimensional well volume. The end of the 3 brane is again a 3 brane sorry, it's a two-brane which has 3 space-time dimensions, and therefore it's codimension free. And therefore is a magnetic source. Indeed, I have 2 objects which can end on the Navier-Schwarz 5 brane. I have the D string. This is the electric excitation. And I have the 3 brane. So at this point, we need to remember that we are in type 2b. The type 2b Navier-Schwarz 5 brane has a U1 gauge symmetry living on its well volume. Therefore, I should expect an electric excitation, magnetic excitation. And those are given by the D string, the D3 brane. So we can now make, using these points, we can make a very highly non-trivial statement about modular spaces, just like we did for the case of theories with 16 supercharges. Let's consider the following configuration. Okay, suppose that I have 2 NS branes and I have n D3 branes. I can look at such a system from 2 different perspectives. The first one is from the point of view of the Navier-Schwarz 5 brane observer. What does the Navier-Schwarz 5 brane observer sees? It sees a U2 gauge tube, which is spontaneously broken to U1 squared. That's back to the adjoint Higgs mechanism that we were discussing before. Any questions about this point? The observer also sees n magnetic excitations or n magnetic objects. They can be in various configurations. All possible configurations that these branes can have will be the space of magnetic solutions, magnetic objects. So in the physics literature, this is called the modular space of K SU2 monopoles. It should be n. Which is known to have a dimension 4 times n. So let's try to talk about it. This could be a logical jump. I didn't explain many things. So the 3 brane here is a magnetic object in an SU2 gauge theory. We know of only one magnetic such excitation. This is the 't Hooft Polyakov monopole solution. Right, so the each such 3 brane, from the point of view of the field theory living on the Navier-Schwarz 5 brane, is interpreted as the classical solution of 't Hooft and Polyakov. Okay, it's the magnetic monopole. Sorry. That's right. Yes. So you did say codimension. It was not a mistake that you said codimension. It's very important to mention the notion of codimension because at Hooft and Polyakov did not really do it in 4 dimensions. They do it in any space-time which has codimension 3. It could be in 3, that's the minimum dimension, and it can go all the way up to 6. In dimensions higher than 6, we don't have interacting gauge theories, and so we stop over there. That's also, well, let me try it. Actually, I take it back. So it's not, you could go also in higher dimensions. You won't have interesting dynamics, but you will still have the classical solution. So as an example, think about dp plus 2 and dp. Right, so it's a dp brane. This can go all the way up to 8. Right, so if this you take to be d8 and this to be d6, there's no problem. It's a perfect string theory configuration where the 6 brane will be viewed as the magnetic excitation of the gauge field which lives on the 8 brane. So it's very important to think about this problem as a codimension 3 object. So I have n codimension 3 objects. Each one of them carries a magnetic charge. The total magnetic charge is n. And the they behave each like a monopole. So I will conclude from this that the space of all possible brane systems that I have in this configuration is the modular space of n SU2 monopoles. Okay? On the boundary, what do you? So if I'm an observer in 5+1 dimensions, the boundary. Why do you say that the modular space has a boundary? It doesn't have a boundary.
I'm saying it's a static condition, a static limit.
Yes.
I'm saying that in the modular of SU2 monopoles of charge n.
Yes.
In the asymptotic, you see n separates one charge monopole.
Yes.
That's what you talk about. N separate.
Yeah, this is when they are separated and the distances are far apart.
But could you and the depth modular has dimension for n.
Yes.
This is asymptotic condition would be less the dimension less or what?
The asymptotics does not change the dimension. Also, when the monopoles are next to each other, after all, the monopole has a size. So if the distance between monopoles is less than the typical size of the magnetic solution, then we start getting effects that of the interaction between the size and the distance, right? And so that's where the approximation of separated monopoles will cease to be a good approximation. So I'll have to use better techniques in order to understand the system where the branes are next to each other or where the magnetic monopoles. So that's an excellent question. So what happens when D-branes start to get near each other? We get gauge enhancements of the symmetry. So let me now talk about the second perspective. This was the first. The second perspective is there is a supersymmetry gauge theory on the world volume of the D3 brane. And this supersymmetric gauge theory is a UN gauge theory with 8 supercharges. So in order to justify for this, I need to go back to the question about boundary conditions and to count moduli. We said that if the branes are infinite, then I have just a theory with 16 supercharges, one vector multiplet which lives on the brane. But if the brane ends over here, I lose some of the moduli because the scalar fields are no longer allowed to move to be anywhere. The brane must be in the place where the 5 brane is located, right? So I cannot put it over here because the 5 brane is not here. So those directions which are transverse to the Navier-Schwarz 5 brane are frozen. But they are frozen in a way which is consistent with supersymmetry, right? So such a system has half of the supersymmetry is broken by DNS branes, and the other half, a different half, is broken by the D3. Altogether, I'll get 1/4 of the supersymmetry which is preserved. I start with 30 supercharges, and therefore I end up with 8 supercharges. So I motivate here for the amount of supercharges. And now, in order to understand what happens to this system, I need to take a 16 supercharge vector multiplet and decompose it to super representations with 8 supercharges. So it divides into a vector multiplet in 8 supercharges and a hypermultiplet. The vector multiplet has a collection of scalars. So we are in 3 dimensions because the effective dimension is such that I'm going to only take into account the fact that this is a small direction, right? So I'm going to take only the 0 mode with respect to the all possible modes which live on the interval, right? I'm going to take a low energy effective description. And the 3 brane initially has 3 + 1 dimensions, but one of the directions is compact. So since it's compact, I can do Fourier expansion. I can take 0 modes. I can take many other modes. And I'll just ignore all of the higher modes and just take the 0 mode. So now I'm in 2 + 1 dimensions. The vector multiplet has a single gauge field and 3 scalars. And the hypermultiplet has 4 scalars. So altogether, I need to figure out which moduli correspond to motion along the Navier-Schwarz 5 brane and which moduli correspond to motion away from the Navier-Schwarz 5 brane. And it turns out that those scalars, I mean, we can compute it, but we don't have the time. Those 3 scalars are along the Navier-Schwarz 5 brane, and those 4 scalars are transverse. And therefore, when I have such a situation, the gauge symmetry survives. The hypermultiplets are projected out by the boundary conditions. So this is where we need the boundary conditions. So we are left with no hypermultiplets, but we are left with vector multiplets. And when they coincide, it gives me a UN gauge theory with 8 supercharges. So this is the bottom line. Now we are out of time, and I'll just say the end of the lecture today. So the Coulomb branch of the UN gauge theory in 2+1 dimensions with 8 supercharges is the modular space of n SU2 monopoles. Just because we have two perspectives and two different observers will compute the same they just look at the same system from two different perspectives. They characterize the same system, and therefore they will have to compare quantities. And so the NS5 observer will see n SU2 monopoles. On the other hand, the 3-brane observer will see a UN gauge theory in a particular point on the Coulomb branch. And so that's why we get this equality. So this is a highly non-trivial result, and we just derived it using the branes. It shows the power that the brane system has in equating very different notions. Thank you.
Unfortunately, we don't have